In this section, I am going to explain you the ASM architecture. For automatic storage management as a product is distributed as part of grid infrastructure product suite starting from 11G. Prior to 11G, ASM in 10G used to be distributed as part of Oracle Database Enterprise Edition CD-ROMs themselves. So earlier there was no bifurcation between RDBMS separately and grid infrastructure separately or ASM separately. It used to be all part of the same software distribution, that is 10G database itself. So creating an ASM instance earlier in the earlier version 10G was somewhat different than the way we do it now in 11G release 2. Now you need to separately purchase licenses for grid infrastructure if you are if you want to implement Oracle Restart capabilities, which is Oracle High Availability Service Daemon or HAS, or if you want ASM, or if you want clustering capabilities, then you need to additionally license grid infrastructure. And database is purely a database now, so you cannot bring up an ASM environment from the database CD-ROM any longer. ASM, however, comprises of these two major components: the ASM instance, and like any other database instance, it's a collection of memory and background processes. While the second larger component that ASM is made up of is the ASM disk group. An ASM disk group is a collection of disks, or it could be partitions or LUNs, which may or may not be protected by RAID, is what we understand by ASM disk group. So the disk that you use, or the partitions or the LUNs, any one of them can be used as part of a participating disk in a disk group. They themselves may or may not be protected by RAID. In general, it's quite unusual in real life to use a disk partition. Nobody will do it, do an ASM implementation like take a disk, create 4 partitions, treat each partition as a separate logical disk, and now club these 4 partitions as disks in a disk group. Nobody would do this in real life. So in real life, if you see, it would either be a disk, or if not a disk, mostly it would be a LUN. So storage team would provision a LUN. It will map it, mask it to a given server, that the given server need to detect those disks. Once those LUNs are detected as disks, they can be further consumed as ASM disks, which will participate in a given ASM disk group. The ASM instance facilitates creating an ASM disk group or deleting a disk group depending on your requirement, adding or removing a disk or disks to a disk group, managing ASM disk groups metadata which is kept in the participating ASM disk itself. Without this metadata, or assuming that the metadata is lost or corrupted, then the ASM instance cannot operate upon the disk group. So metadata is very critical for an ASM disk group's operation. Creation of continuing operations directory, abbreviated as COD, when a database instance requests file creation on a ASM disk group. Maintaining the active change directory, which is abbreviated as ACD. Performing IO rebalancing when a new disk is added to an existing disk group, or when an existing disk is removed from a disk group. In either cases, ASM would perform an IO rebalancing activity. In the absence of IO rebalancing, you might end up categorizing your disk as hot, warm and cold. To avoid this, ASM would anyways perform an IO rebalancing act whenever a new disk is added to an existing disk group, or when an existing disk is removed from a disk group. However, that activity in certain cases can be deferred. If you don't want to do it immediately, you can say do it at a later time. But that option is not available in all the cases. It's available only when you add a new disk to a disk group. Instead of doing the rebalancing immediately, you can say do it at off-peak hours. But while removing a disk, there is no such option available. While removing a disk, you can't say that don't do a rebalancing, do it when there's nobody else connected to the database. IO rebalancing is evident and cannot be avoided in case of removal of a disk. But while adding a disk, you can at least defer that activity. It ASM instance also facilitates in mounting of disk groups during the instance startup. So whenever your instance starts, automatically all the disk groups that you would want to be automatically mounted can be automatically mounted. Now there's a way to tell an ASM instance which of the available disk groups you would like to mount using some init aura parameter that we are going to discuss anyways shortly. Creation of ASM volumes inside ASM disk group is also facilitated by your ASM instance. Recovery of ASM disk groups data in case of ASM instance crash using ASM transient logs are all the jobs that are performed by your ASM instance. So if you see, no user as such would connect to ASM. No user would run an end user transaction on an ASM. This is what is peculiar with a database instance. People, end users, applications would often connect to a database instance. They would run their transaction on a database instance. Database internally talks to ASM. And whatever is required to facilitate that communication, ASM is promptly available there to do the necessary background activities for a database. That doesn't, however, means that whenever an IO has to be performed, the IO would be performed by ASM. No. So ASM would not do a proxy IO on the behalf of your database instance. Database has to anyways write its own data onto a ASM disk group. However, to make that happen, whatever is required by the DB writer process would be provided by ASM, rather the information. ASM instance, like any other instance, requires a parameter file, which could be either a P file or an SP file during startup. The parameters with respect to ASM are, however, very limited. You don't have close to 300 odd parameters like you have in case of a database instance. The most important ones that distinguishes this instance from any other RDBMS instance is the init aura parameter instance underscore type. The default value of this parameter is database. That's why you don't mention this parameter in the P file. Because anyways, if the parameter has a default value, there is no need for you to again categorically add that parameter in the parameter file. We had this discussion earlier. Only when your default value does not applies in your case, you would like to override that value. Could you hold that for some time after the class? Instance underscore type in case of an ASM categorically overrides the default value RDBMS, and that's why you need to mention this in case of a parameter file of an ASM instance saying instance type is ASM, because if you don't mention, it will be treated like an RDBMS instance. Instance underscore name in case of a non-rack implementation would often be plus ASM, and positively utilize your energy by not discovering what's the reason behind that plus. So instance name in case of a non-rack implementation would be plus ASM, and for rack implementation it would be plus ASM1 plus ASM2 and so on and so forth, depending upon how many nodes you have in your cluster. Memory target, when not mentioned, would default to 272 MB, which also means that ASM uses 11G style of automatic memory management. Within this 272 MB is most often more than sufficient for all types of ASM implementation. So what's the additional workload or footprint that ASM adds on a server? It's only taxing to a limit of 272 MB, which is a very less memory consumption when compared to the amount of available RAM on the server. So it's very less as far as the taxing part is concerned. The only other memory component that you might want to explicitly define is large pool. Large pool of 12 MB is more than sufficient. Large pool in case of database, and same also applies to an ASM. Memory is used for buffering the additional work that gets generated in case of a master slave relationship, or in case of simulating an asynchronous IO operation. For a database, when you take a backup to a tape device, to be able to keep on that tape spooling and to optimize the latency that a tape has with the speed of your CPU, that whole optimization happens by allocating IO buffers. That IO buffer is a memory region allocated from large pool. Similar way, whenever you try to simulate an asynchronous IO operation on a platform which does not inherently support asynchronous IO, in such cases multiple slave processes would do an IO operation. Now each slave process would allocate some amount of memory in the form of buffers, which can be then allocated from large pool. Other than this, large pool is optional. Consider a case where on a given operating system platform, asynchronous IO is not supported. So that means by default the operating system would only offer you a synchronous IO. Synchronous IO, due to its very nature of adjusting the speed of an IO to the lowest receiver or the slowest receiver, makes it very problematic at times. So I said write down an 8 KB block onto a disk is often achieved via DB writer. The DB writer would adjust its speed depending upon the slow disk IO controller. Now this might be a point of bottleneck when several hundreds of dirty buffers are to be written out to the disk. In such cases, where platform does not or has a built-in support for asynchronous IO operation, we often enable DBWR IO slave processes. The DBWR IO slave processes are not as technically strong as the DB writer process. The only job of the slave is to receive a list of dirty buffers and write them to the respective data files and confirm the status back to the master. The master in all the cases would be the database writer process. So the database writer process will scan the database buffer cache, both standard and non-standard, keep and recycle, all inclusive. It will prepare a list of dirty buffers to be written down called as a dirty list, which is also a data structure in your SGA. Once the dirty list is populated, database writer itself write it down. But assume a case that I want to speed up the writing operation. Then there are two ways of doing it. Start multiple database writer processes. If not, start only one database writer with multiple slaves by doing DBWR IO slaves parameter. So automatically slave processes are spawned, in which case the only job of database writer is to collect and maintain dirty list. Once a dirty list is prepared, at a next checkpoint or whenever the next dirty write event occurs, DB writer will just divide that entire list into amongst the slave processes. The slave processes will do the actual work of writing down those dirty buffers to the respective disks and would report back the status to the database writer. As against another model where somebody may want to start multiple database writer processes itself. But as a rule of a thumb, Oracle recommends 1 DB writer for every 8 CPUs that you have in your machine. Now if you try to disregard that and you would like to still start multiple database writer processes, probably the taxing of a system resource is more than the benefit that it offers. So in such cases where you would not like to start a fully functional database writer process, you can always simulate an asynchronous IO operation by starting DBWR IO slaves. So whenever there is a master to slave relationship for simulating asynchronous IO operation, whether it's while doing a tape backup using RMAN allocated channels, or whether it's writing using a DBWR IO slaves, buffers needs to be allocated. The buffer is a temporary memory region which will be utilized by those IO slave processes, and such memory is allocated from large pool. In which case the block will be corrupted. Mhm. Correct. Correct. No, blocks don't corrupt just because of an asynchronous IO. I will explain. When you write the data, there are two ways of writing. It's like, I'm pausing this video as. Next is ASM power limit. ASM power limit is the degree of parallelism while doing rebalancing. How many worker processes you would like to use for doing parallel rebalancing? So as you have got an enormously sized disk group which has got say 120 disks. Now I added 4 new disks to the disk group because I am anticipating data growth, and to sufficiently size my ASM disk group, I plan to add new 4 disks to the disk group which already has 120 disks. So the moment I add them, it will trigger the rebalancing. Now question is, how would you like to approach the rebalancing? Using one slave process at a time, two slave processes at a time, three slave processes at a time, at the max 11 slave processes at a time. So you can run that rebalancing activity using 11 rebalancing processes. Now again, this whole rebalancing is like a master slave process. The master is the arbal process, stands for rebalancer, while the slave processes are ARBN, which stands for actual rebalancers. You can have up to 11 rebalancer processes. Now whenever the disk group geometry changes, meaning I am adding a new disk to a disk group or I am removing a disk from a disk group, the whole disk group geometry has changed. Now whenever this happens, Oracle, to balance the IO on all the participating disks in an ASM disk group, automatically triggers the rebalancing. Now how would you like to do that rebalancing? With multiple slave processes or with one slave process? So if you rebalance with one slave, if you rebalance with one slave process, the rebalancing act will take a longer time, but the IO impact because of rebalancing would be negligible. If you fire 11 rebalancers, which is the, in a worst possible case, you can go for 11 rebalancers. The rebalancing would finish quickly, but the IO impact will be higher. So it's a race between what you want more. It's a quicker rebalancing as against the IO impact. People, some of them may say, I would not like to do rebalancing immediately. I will do it manually at off peak hours, in which case you can set the ASM power limit to 0, which means do not trigger auto rebalancing. And whenever off peak hour arrives, typically a night time slog period, then I might say alter disk group something like this. So I can then manually, so I can defer the rebalancing, auto rebalancing by setting the ASM power limit to 0. And later on at off peak hours, then I can manually trigger the rebalancing so that the IO impact would either be negligible or would be at that time when there nobody around to complain about the IO impact. So ASM power limit. Next one is cluster database is equal to true. Although it says database, it still applies to ASM, which means the same disk group would be mounted by more than one instances, which is otherwise not possible if you don't set this parameter. So now you have ASM instance 1 running on alpha, ASM instance 2 running on beta, but both the ASM instances have mounted the same disk group plus data in our case. So this is only possible because clustered database is set to true for clustered ASM implementation. Next could be next parameter is ASM disk string. It is nothing but a pattern matching string which helps ASM instance to locate the probable disks during instance startup. Now each operating system keeps the disk in its own proprietary device location. Say for example, all the raw devices in case of AIX are kept with the name slash dev slash rh disk whatever, rh disk 1, 2, 3, so on and so forth. In case of Solaris, the raw devices are kept in the directory slash dev slash rdsk, and the name of the disk themselves would be something of this form: cn, tn, dn, sn, where C indicates the controller, T indicates the target, D indicates the device associated with that target, S indicates a splice, which means a partition, if at all a disk is partition. So which controller, which target, which device, which disk, and which partition on that disk is how the naming convention Solaris follows. In case of Linux, I'm talking about the old days implementation where Linux used to support raw devices. The raw devices in case of Linux were kept in the directory slash dev slash raw star, where that star can be replaced as raw 1, raw 2, raw 3, raw 255, so on and so forth. Linux nowadays does not support raw devices any longer. There is no kernel built-in support, native support for creation of raw devices. Instead, Linux nowadays supports, this is off the track discussion. Linux deprecated the rather 2.6. Linux deprecated support for raw devices starting from kernel version 2.6. Prior to that, Linux also used to support limited number of raw devices, 255, but not more than that. Starting from kernel version 2.6, Linux only allows block devices. So no more character devices or raw devices, disk devices are allowed. Linux nowadays only allows you only one type of a disk, and that is a block device. No more character or a raw device. But they have made a significant change in the way the API of write happens. So for example, Linux provides an API write pointer to a buffer and the file handle. Which buffer needs to be written and in which file handle was the earlier API. Now in case of a raw write, there was only file handle. Just write the data to a file, no more buffer. Nowadays Linux has deprecated this. Now it says there is only one way of doing a write, which is optionally followed by a flag O direct. Do you want to write using a buffer to a file, or you want to bypass a buffer and write to a file? O direct flag simulates bypassing a buffer and directly dumping the data to a disk file. This is what was the use of raw devices earlier. A block device utilizes I/O buffers, while a raw device bypasses an I/O buffer. But Linux says for that you don't need to create two different types of devices. Like one of the famous scientists, he created two holes in the door, one for the baby kitten and for the cat. He said you don't need that way. A bigger hole could have subsided or would have sufficed in this case. It says if you want to simulate a raw I/O, just pass a third argument as O direct. If you do not want to enable or you want to enable a general I/O, simply do not add that O direct tag. Same block devices can be used for simulating a raw I/O. For that you don't need to create a separate set of raw devices. In which case there would be no raw devices. So in case of Linux, with block devices and with Oracle supplied software called as ASM lib, the device specific location will be ORCL colon. So where are the devices? That ASM lib will tell you. That's why the identifier, the pattern matching string says ORCL colon. Meaning go to the ASM lib directory or software. The ASM lib software will tell you which all disks are available. Remember, etc init.d Oracle ASM list disks gives you the list of all available ASM disks. That is possible because of ASM lib software. Primarily, ASM lib was designed to stamp a disk for SCSI persistence. ASM lib module Oracle developed it because in case of Linux there is no SCSI persistence. So whatever learn today shows me the device name as /dev/sdb, there is no guarantee that tomorrow also after a reboot the same learn will be detected as /dev/sdb. It might show you some other name /dev/sdc. So there is no SCSI persistence available by default. Now to guarantee that the same device name gets bound to the same learn, you must use some kind of a SCSI persistent technique. This problem was inherently there in case of Linux, to which Dell in 2004 developed a module called as dev label, which later Linux incorporated using its own proprietary style, using udev rules. And if you don't want to use both, you can use ASM lib. So it's not that you need to use ASM lib. It's only Oracle way of doing the SCSI persistence. And Oracle says if anyways you are implementing it on Linux, which does not nowadays support raw devices, then instead of using a third party dev label or Linux's own udev rules capability, you can use our own module called as ASM lib, which is anyways free. So depending on the implementation, depending on the operating system, where should ASM instance look for probable participating ASM disks is what is identified by ASM underscore disk string. So during instance startup, Oracle needs to mount a disk group. For that disk, there must be disks which must be participating in that disk group. Where should that ASM instance look for participating disk is what you mention in ASM disk string. So ASM instance goes to that directory. Whatever devices are available there, it scans them. It reads the first few bytes of that disk to find out whether or not this disk belongs to ASM or non-ASM. If it belongs to ASM, then to which disk group it is participant of. It gets this information during instance startup, and where to look for those disks is mentioned using ASM underscore disk string init aura parameter. Clear? Next one is ASM disk group. Now one ASM instance can have as many as 64 disk groups. One ASM instance can handle 64 disk groups. Now not all of them you would like to auto mount. Only few of them you would like to auto mount. In which case the ones that you would like to auto mount must be mentioned as part of the init aura parameter value ASM underscore disk group. So I said I have 10 disk group, but out of which I just want to auto mount data, redo and FRA. Assuming data, redo and FRA are the name of the disk groups that I have created earlier. Remaining 7, although they are there, but I don't want to auto mount them. There is, however, an exception to this rule. So which disk groups would be auto mounted? The disk groups that you have mentioned in the init aura parameter ASM underscore disk groups. The exception to these rules are these ones. If a particular disk group holds an ASM instances SP file, so whether or not you list that disk group in the ASM underscore disk group parameter, it would still be auto mounted. If a ASM disk group holds a copy of voting disk or an OCR for that matter, whether or not that the disk group is listed in ASM underscore disk group parameter, it would still be auto mounted. Clear? Very important. So there is no need for you to explicitly mention such disk groups as part of the init aura parameter value. They would anyways be auto mounted. ASM environment would not have its own control file, data file, temporary files or redo logs for that matter. None of these files apply to your ASM instance or ASM environment. For ASM you only have a parameter file, and in a worst case, in the other case you would have log and trace file. So there will be an alert log, there will be a background trace files, but nothing more than this. All the data that would have otherwise come from a control file or a data file of system tablespace for a regular database instance comes from metadata, which is stored in the ASM disk in case of ASM instance. So what normally is stored in a control file? Control information. What is stored in a system data file? A data dictionary. So there is no such thing applicable in case of an ASM instance. All that ASM instance presents to you is coming from metadata, which is written into the participating disk of a given disk group. Now when I say this, it automatically highlights one point, which means ASM does not have any static data dictionary views, because static data dictionary views display information from data dictionary base tables. So there are no base tables, there is no data dictionary, there is no system table space. That means all the views that you would query ultimately in case of an ASM instance are all dynamic performance views. so on and so forth. So there would be no static data dictionary views. All those views that you see in case of an ASM are all dynamic performance views. So they would display the information that is otherwise stored in a form of a disk metadata. Now when it comes to disk group, we must elaborate further, because disk group is not just simply a collection of disks. Disk group is a collection of disks, partitions, LUNs, which may or may not be protected by RAID levels. However, at an ASM level, you can opt for some redundancy settings for a disk group. If you select the ASM redundancy setting as external, it means ASM software would not maintain any redundancy of the data that it writes into this disk group. So consider a case that my disk group has 4 ASM disks, and those disks are not protected themselves by RAID. I club them together in a disk group called as data. So whatever data I store in this disk group will be striped across all the 4 participating disks. If one of the disks fails, my entire disk group fails. This is quite similar to RAID level 0. What is important to understand, somewhere I made a point in earlier discussion. I think during fault tolerance, this point, ASM stripes data on all the participating disks in a disk group in case of external redundancy. So the data that you store on a disk group will be striped across all the 4 participating disks. So if the disks themselves are not protected by RAID at a hardware level, and if one of the disks fails, the entire ASM disk group fails. However, in case of a normal and a high redundancy, ASM still stripes the data, but not amongst all the participating disks in a disk group. This time it stripes the data in a failure group. So that we'll see what is a failure group. The second level of redundancy setting possible for ASM is normal redundancy. In a normal redundancy, the data that you write onto a given disk group is written twice across failure groups and striped amongst disks within a failure group. So assume that in a given ASM disk group, let's say I have a disk group with the name DG norm which has 8 disks. Those 8 disks I have divided as 4 disks in failure group 1 and 4 disks in failure group 2. When I write some data to this particular disk group DG norm, I stored one file. My file will be broken into pieces and those pieces will be scattered across 4 disks in one particular failure group. And then those same pieces are redundantly written in another failure group. So if one of the disk fails, the other failure group can be used to retrieve the data. So you achieve striping within the disks in a failure group and you achieve redundancy by writing the same data across the failure group. So that's what I mentioned here, which means any data written to this disk group would be written twice across failure groups and striped amongst the disk within a failure group. If you don't want some files to be redundantly written, you can make an exception using custom defined templates. So if you store a file, if the disk group's redundancy style is normal, any file will be written twice. I don't want some of the files to be written twice. Then create your own custom template. And while creating a file on this disk group, you will come to know during practicals anyways. But while storing this file, use your custom defined template. So that file in particular will not be written twice. This is why I said it's otherwise as good as RAID level 1, but it's slightly intelligent than RAID level 1. RAID level 1 is purely disk to disk mirroring. Here you can decide on the basis of contents that you would like to mirror and the contents that you would not like to mirror. So while storing my files, if I don't say anything, my file will be written twice. First it will be written in a striped manner in one failure group, and then the same stripes will be replicated in another failure group. Both these failure groups are part of my disk group, let's say DG norm. So you achieve striping for improved IO bandwidth, and you also go for redundancy for fault tolerance. But consider a case that I am using an externally redundant disk group, and there are 4 disks, but those 4 disks are themselves hardware RAID protected. So if one disk is lost, yes, so those disks themselves are hardware protected, RAID level protected. So if one of the disk is lost, your ASM disk group will still be up and running, right? Because the failure of a disk at a storage level will anyways be transparent to my ASM. A disk has failed, who cares? I am not worried about a disk. I am worried about a LUN, and LUN is still anyways fault tolerant. So remember the way we have configured the NetApp filer simulator? We configured it by putting 24 disk in RAID 4 protection. So if any of the 24 disk fails, there is no impact to your LUN. Since there is no impact to the LUN, even if creating such 3 LUNs, I create a disk group, even if one of the disks fails at a storage, my LUN is still intact, which means my ASM disk group is still intact. Clear? So that external simply means ASM would not do anything special to make the data redundant. If the disks themselves at a hardware level are redundant, then the data will not be lost when a single disk fails. But if the disks themselves are unprotected and one of the disks fails, since ASM is not doing categorically anything different to make the data redundant, then the whole disk group will be lost on once you experience a single disk failure. Sorry. Mhm. If the disks are anyways protected, reconfiguring a protection at an ASM level simply can be done by Ambanis. That means you are spending double the disk space. It's like that same Santa Singh carrying two railway tickets and a pass. So it's that means you are spending on disk space or more. Anyways, I gave you two disks which are internally mirrored. Then I gave you said they are normal. So data is written here, which is actually going to 2 days. Data is redundant here, which is actually going to 2 days, which means that the cost per storage byte is 4 times. So when the hardware is, when the disks are anyways protected at a RAID level, go for external redundancy. If they are not protected at a hardware level, then depending on your budget and the type of protection desired, go for normal or high redundancy. To configure a disk group with normal redundancy, you need to define minimum two failure groups. A failure group is a subgroup inside a disk group. Finally, if my disk group has 8 disks and I have decided to create two failure groups of 4 disks each, so a failure group 1 will have 4 disks, failure group 2 will have 4 disks, and altogetherly these two failure groups, 8 disks, are part of your disk group, say DG norm. High redundancy for a disk group offers three-way protection. Means the data will be written thrice. So if one disk fails, the other failure group fails, still the data is redundantly available, which is very uncommon in real life, but somebody with a focused usage can still use it. For example, I want to go for redo log multiplexing, control file multiplexing, where I would like to maintain 3 copies of control files or 3 members in a given redo log group. Then instead of going for Oracle level configuration, store one group with 1 member on a disk group which has a higher protection. So anyways, it will have 3 disks involved, 3 copies will be written. So high redundancy offers three-way protection. Data that goes to this disk group would be written thrice across failure groups and striped on disks inside a failure group. So whatever data you store, it will be striped amongst the participating disk in a failure group, and the same data will be replicated once and twice across failure groups. So even if multiple disk fails now, the data can still be safely extracted from one of the surviving disk groups. To configure a disk group with high redundancy, you need to define minimum 3 failure groups. And as always I said earlier, a failure group is a subgroup inside a disk group. Clear? So consider a case that I am opting for a high redundancy configuration. So I created 3 failure groups, FG1, FG2, FG3, and each of those failure groups is populated with 4 ASM disks. But what is the usage percentage now? 33. The investment done in the disk as to the returns I get on that disk is only 33% returns. In case of DG norms, it is 50% return. And in case of DG external or external redundancy, assuming there is no RAID protection, it's a 100% return. If the disks are externally protected by RAID level, then again it is 50% economy, or the ratio to investment as to the usage is 50%. Now comes the question. I am creating a disk group, say DG data. While creating, I selected normal redundancy and I added 12 disks to this disk group, and I split those disks like this. Understand this, my question first. I am creating a disk group named DG data. Redundancy selected for this disk group is normal. I added 12 disks to that disk group. Later I distributed those 12 disks by creating 3 failure groups. Each one of them would receive 4 disks. If I store a file now on this disk group, how many times the file would be written? Pause. So since the disk group redundancy style is normal, now the minimum number of failure groups for to be there for creating a disk group with normal redundancy is 2. But remember, I have highlighted the word minimum. So minimum it should be 2. It could be more than that, but that doesn't changes the style from normal to high. So just I created a disk group with a normal redundancy style with 3 failure groups doesn't changes the intrinsic behavior of two-way mirroring to a three-way mirroring. Otherwise, what could have been the difference between a normal and a high redundancy? That's where the question is important. So any data that goes on to this disk group will be written only twice. Now the question is, how is this possible? So if it writes the data here, it will mirror here. If it writes the data here, it will mirror it here. If it writes the data here, it will mirror it here. How does it matter? So let it write anywhere in one failure group. Let it mirror anywhere else across any other failure group. Disk utilization percentage still is 50%. So it doesn't matter just because there are odd number of disk groups that I would end up doing something else. If data is written in one failure group, it will be redundant in any one of the two. If it is written here, then it will be a redundant copy would either be written here or here. Anyways, what do we want to achieve? Two-way write should happen. The two writes should not happen in the same failure group. they must be across failure groups, and data should be striped across disk within a failure group that you are achieving anyways. So the disk utilization percentage would still be 50%. Am I clear? So the disk group redundancy. Now the status of a disk. Now while creating a disk group, you would be looking for probable disks that can be added to a disk group. You would be looking for some free disks, but there is nothing called as free. The statuses are different. You must understand which disk can be a probable candidate for a new disk addition type of an operation. So a disk group status might show you candidate, which means a fresh disk ready to be consumed. This is typically a raw device which has just been commissioned. So you can readily consume this particular disk. The status provision means a fresh disk ready to be consumed but provisioned with ASM lib. By provision with ASM lib means you must have done earlier stamping of those disks by saying etc init.d oracle ASM create disk ASM disk1 slash dev slash sdb1. So that disk was stamped, the header was stamped, and the disk was reserved. When you try to look at all the disk in a given location, if some disk shows you status as provisioned, it means this is a freshly created disk and it has been provisioned for ASM usage. Member, a disk which is already part of some active disk group will show the disk status as member. Former, a disk which was earlier part of some disk group but is now free. Probably that disk could have been removed from the disk group or the disk group itself could have been dropped. So that's why the status shows former. If the status of a disk shows as foreign, it means a disk which is being used actively outside the premises of ASM, probably by some other application. So now, which of these disk statuses are of use when it comes to deciding upon which disk I can use for new ASM disk group creation? Candidate, provision, or former. Member and foreign disk cannot be used. Member disk means it's currently being used. Foreign disk is being used but outside the scope of ASM. Now, candidate and provision are mutually exclusive. So you will either see candidate disk or provision disk, because you cannot club the style of using the raw devices as well as with ASM lib. So you will have to use either style. So if you use the raw devices style, you will see candidate. If you use ASM lib way of doing a ASM disk group creation or provisioning of a disk, then in that case the disk status will show you as provision. Clear? You can obtain these disk statuses from $ASM disk. So there is a command also which you can type, lsdsk, which has to be typed on ASM command prompt. ASM command prompt, ASM offers you an utility called as ASM command line utility, ASM CMD. Once on the ASM CMD command prompt, you can type a command lsdsk to obtain the disk status. If you are connected to SQL Star Plus, you can query $ASM underscore disk to obtain the disk statuses. Remember, ASM scans for probable disks in a given path which we have already provided using ASM underscore disk string init aura parameter. That time it comes to know what is the status of a disk. Clear? So it's during the startup that ASM comes to know if a given disk is candidate, provision, member, former or a foreign disk. Next is understanding the startup of an ASM instance. This is how the chronology is. It reads the parameter file, starts background processes and allocates memory for instance operation. This state we often identify as no mount state. Next is the chronology of ASM instance startup. It reads the parameter file, starts background processes and allocates memory for instance operation. This state once achieved is called as a no mount state. It reads all the disk headers in a given location. The location is identified by ASM underscore disk string and prepares a list of probable disks available at that location. It determines which disks are available for a given disk group and then mounts all the possible disk groups that you mentioned in the ASM underscore disk group parameter. Once achieved, this state is called as a mounted state. ASM instance stops here. So there is no open state for ASM instance. At the max, an ASM instance goes to a mounted state, which is considerably different than the way an RDBMS instance mounts the database. By mounting of an RDBMS instance, we say that that particular instance categorically marks in the control file that I would be mounting the database. Here there is no control file. There is no locking of control file. So it purely just mounts the given disk group. However, the mounting of a disk group can be a shared mounting or exclusive mounting. If the init or a parameter cluster underscore database is not mentioned, that means default value is false, in which case the ASM instance will mount the disk group in a exclusive mode. If however cluster underscore database parameter is true, the mounting of a disk group would be a shared mounting. Clear?